when we move to predicting the product, when we are given this particular reaction beginning step, we see that this particular compound is going to be reacting with the sodium ethoxide in the presence of ethanol. And so in this part, we are going to see what are the two products. How are we going to prove that letter A and letter B are formed? And we are going to prove that through two competing mechanisms that relies heavily on the function of the sodium ethoxide. And so what sodium ethoxide can do are two things. One is that sodium ethoxide, which is also written as this, can do two things. One is that it can act here as a nucleophile, and in here a nucleophile is a compound or a species that one is considered to be a really good electron rich species, and it is or can be noticed to have either a negative charge or neutral regions around it. And this is in terms of the charge. And next is that the lone pairs are really good at creating a bond, and this is really important because the bond is known to be a covalent bond. And finally here, this nucleophile acts or is also called a Lewis base. And while the other competing state of ethoxide is that it can act as a base, and this base, usually we call this type of base a busted base. And this busted base always does the following: they accept a proton, and the acceptance of a proton is actually gotten from an acid, and this process is usually a neutralization reaction process. And so this is really important to distinguish and remember. These are going to be competing against each other in terms of whether A is on the side of a base reaction and the formation of B is from the side of a nucleophile reaction, or vice versa. So let's dive into the next step. The next step is to look at how the ethoxide is going to be acting as a nucleophile in this reaction. And what we are able to investigate is what region is a nucleophile going to be focusing on in our main reagent. And what we see is that by exploring all regions around this particular compound, we observe that, hey, there is a specific carbon that is of great interest, and this carbon is called the alpha carbon, which is directly connected to a good leaving group, which is in this case bromide. And so this alpha carbon is of interest for our nucleophile because in this case it's going to act as a good bond formation in here, but then results in the leaving of our bromide. So this process here is going to be called a bimolecular substitution reaction. And when we arrive at our specific mechanism for this, we see that first our main reactant, which is in the presence of our ethoxide, this lone pair is going to be creating a bond with this carbon, alpha carbon, and while the alpha carbon bond with this bromide will cleave to form a lone pair on the bromide as the bromide leaves to form a negatively charged species. Looking at this in terms of the transition state, how is this going to look like? Looking at the transition state, what we see is that by short form we have the bracket with our specific symbol that this is a transition state, this shows that on the plane there is hydrogen bonded to, in this case, away to the carbon, and we have the other hydrogen right here, and on this other side we have the R group, which represents this segment of our species. This is going to show that at the top we're going to have the formation of our ethoxide bond, which has a dipole negative on the oxygen component, while on this other part here we have the breaking of our bromide bond, and this will also have a negative dipole moment. As a result of that, this will lead to the formation of our product, which is as follows. Take note here that our bromide is going to have a negative charge that is bonded to our sodium, and therefore this reaction here indicates that this is called a SN2 reaction. The reason why this is an SN2 reaction because it is a bimolecular reaction, looking at it at the transition state where as one bond is being formed, the other bond is broken down, which requires two of these compounds to be interacting with each other in order for the formation of this bond to be created, which is right over here. And also we have non-formation of a pi bond, which in this case leads to one reagent being substituted for another reagent. Now the next part is looking at ethoxide acting as a weak base, and through our analysis we need to find a region which is actually found between our alpha carbon and the carbon next to the alpha carbon, and this carbon here is called the beta carbon. And this beta carbon is really important because it has specific hydrogen atoms that will be important in terms of this particular reaction to be enhanced. And this beta carbon here, looking at these in terms of highlighting the two hydrogens, will be instrumental in this process, because in this case we are going to be performing a reaction that is called a bimolecular elimination reaction, where as a result of this, our main reactant here is going to be subjected to the deprotonation of our species here in this beta carbon region due to the presence of our ethoxide. Therefore, what happens is that this lone pair comes in here and picks up this hydrogen atom. Therefore, the carbon hydrogen bond cleaves to form a pi bond here, and this particular carbon bromide bond cleaves to form a lone pair on the bromide. Therefore, by drawing our transition state, we see that there is the breakage and formation of bonds that is continually happening right over here, where our R group represents this region here, and this here is going to be bonded to the hydrogen that is not involved in the deprotonation. However, we have this sigma bond that is going to be maintained. However, we're going to have our bromide, which will have a negative dipole moment, and as this bond is breaking off, we have the formation of our pi bond right over here. Remember that this has a dipole positive, and this now leads to the breakage of our hydrogen bond, which has a dipole positive, and remember that this has a dipole negative, and therefore our hydrogen oxygen bond is going to be formed right here, which has a negative dipole moment, and this shows you the ethyl group that is left right over there. Now remember also that this region do have a hydrogen atom, and not one but two hydrogen atoms, so that is something to be mindful of, and this here leads to the formation of our product, where in this region here between the alpha and the beta carbon we have a pi bond that is created, while the other side products includes ethanol, which is shown right here, and finally we have our sodium bromide that is going to be formed right over here. Now remember that this process here, or this reaction of focus, due to the presence of ethoxide acting as a weak base, is known to be called the elimination or E2 reaction. And this is the E2 reaction because in here we have the elimination of our hydrogen and our bromide, which is a good leaving group, and this leads to the formation of a pi bond that is right here. Take note also that this elimination process is a bimolecular step because you need these interactions to be occurring at the same time in order for the formation of our pi bond to be established. Remember that the transition state here is not also negative here, but also negative at this particular SN2 reaction transition state. So we're going to have this to be highlighted right there. Based on our starting reaction, our B is the middle spot that is right over here, and this is our starting species that is really easy to take care of. Now between A and C, which one above and below is A and which one is C? This comes down to going to our chart, and in our chart the one that is higher is the alkene, and the alkene here implies that yes indeed this here is our C species, and while our ether, which has the oxygen present, which will have hydrogen bonding with our silica gel and also a little bit of dipole interaction, yes, will be interacting less with our solvent and more with our silica gel, and this will be labeled as A. Now we have determined the products of this particular reaction, which shows that there is a competing formation of products. One is the formation based on an SN2 reaction, while the other one here is produced through an E2 reaction. We need to be able to understand how to favor one reaction over the other reaction. In this case, we need to first look at how SN2 reactions is favored and how this stands out with E2 reactions. And so first is to keep in mind is that for both reactions to be favorable, they share two things. One is that they rely heavily on polar aprotic solvents, and the other part here is that they require good leaving group. And those are the two things that they both share in terms of favorability. However, the distinguishing factors between the SN2 and the E2, looking at SN2 first, is that for SN2, this depends heavily on using a primary alpha carbon, and this is way more favorable than that of a secondary alpha carbon. And this is really important to remember for SN2 reactions. However, for E2 reaction, this is favorable using a particular anti-periplanar beta hydrogen, and that is really a great criteria to remember for favoring E2 reaction. Next here to keep in mind is that for SN2 reaction, you need a really good nucleophile, and this is really important to keep in mind because you don't want a strong base to be involved in an SN2 reaction. Otherwise, you're going to be deprotonating a specific hydrogen, which you don't want for SN2 reaction. However, for E2 reaction, you need a strong base, and this is really important to facilitate the deprotonation of a carbon, which in this case is a beta carbon that has the hydrogen present that is anti-periplanar. Next is that for SN2 reaction, this requires a weak base which feeds off of the good nucleophile, while on the other hand, looking at E2 reaction, we said that not only are we required to have a strong base, but most importantly, it must be done in the presence of heat. Without heat, you're not going to be favoring a reaction that is E2 like reaction. And so moving back to this question, which says that how are we going to be able to favor this particular reaction that leads to the formation of this particular product. In order for we to achieve this, what we need to remember are three things to keep in mind. One is that instead of using this solvent, which is ethanol, we are required to use methanol as our solvent. And once you're able to make that change, this must be accompanied with a bulky strong base, and a bulky strong base instead of this particular base, which is weak base, of course, will enhance the formation of this E2 product. Therefore, such bulky strong base will be in the form of this particular species, and in here we have this carbon to have not one, not two, but three carbons attached to it, and this is really interesting to actually take care of. And next one here, and the final one to keep in mind in terms of favoring E2 reaction, is applying heat. All the same, thanks for following me through this. Truly appreciate it. Hit a comment down below. Let me hear your thoughts about this. By that way, I can talk to you all soon. Stay smart as always and believe in yourselves.